So now that you're motivated, we can actually talk about net surface heat fluxes. We focus at the surface. But before we do that, let's just have a little recap about what you already learned. So you can, if you look at textbooks, you find sketches like this one here. Okay, it shows you the atmospheric heat budget and surface heat fluxes. So let's have a look what's included here, maybe just as a summary of previous lectures. Just a little bit, okay? So you have incoming solar radiation, okay, at the top of the atmosphere, average 342 watts per square meter, okay? This is shown here. In this sketch, you also have the albedo effect. That's the albedo effect here on the left side, all right? What's also shown here is the greenhouse gases. You have the back radiation in this sketch. You have the atmospheric window. You have the surface radiation in here. You have also clouds, cloud effects, and so on, and the outgoing long-wave radiation. So this one summarized pretty much most things that we have done, apart from some details, some additional features of the surface heat flux. This is featured here. So we want to look at the surface heat flux because the surface heat flux includes additional terms. Okay, it includes heat fluxes that come from evapotranspiration, which are featured here, and heat fluxes that are called thermals in here. Okay, let's focus on the surface heat flux budget in more detail. Here we go. This is the residual surface heat flux. Okay? And the naming is a little bit different compared to what we had before. The reason why these symbols are different is that I want to show you a table and a figure taken from the Hartmann book, and Hartmann uses these definitions and these names. So here what we call Q net in this equation, which is shown here at the top, is the net surface heat flux. And this is just the sum of all terms that are written on the right-hand side of this equation. If the right-hand side of this equation is 0, means there is no heat flux and the temperature does not change of your substance. Okay, if it's positive, your substance will become warmer. If it's negative, your substance will cool down. Okay, this is written up here on the right. Oops. And just as a note, if you think about the oceans, you can have compensating effects by horizontal currents that might also compensate for a cooling effect by bringing warmer water into the region. So this discussion is only correct if you just ignore effects by oceanic currents. Anyway, so this is what's here. Then on the right-hand side, what do we have? We have RS, and this is the net radiative flux of energy. This is radiation. It has two components: shortwave radiation from the sun, long-wave radiation emitted by the surface of Earth. And we talked about it, just the names are different here. One is called SW and the other one is called LW. Okay, here we go. We talked about this, but now there are two additional terms. One is called LH and one is called SH. LH is the latent heat flux due to evaporation, and SH is the sensible heat flux, the direct heat transfer. Okay, so these two additional terms influence the surface heat flux. Okay, and they play actually a big role in the surface heat flux, as you will see. Okay, let's just in more detail talk about these latent and sensible heat fluxes. So the latent heat flux, latent heat flux is associated with evaporation. Okay, it's actually directly proportional to the evaporation rate. Okay, evaporation gives you a heat flux. So this flux depends on the air-ground difference in relative humidity. It depends on the wind speed too. If you have no wind, there will be no evaporation. And the wind speed determines you of essentially how much is evaporated. Okay. The latent heat flux has always a cooling effect. That's a very important thing. So if you have evaporation, it always has a cooling effect. Okay? On its own, the latent heat flux. And this is what you notice if you're sweaty on your bike and you are riding down the hill and you have that relative wind effect, and it's a wind chill effect. You know, it feels cold on your skin, and this is the cooling effect. The other feature is the sensible heat flux, which depends on the air-ground difference in temperatures. Temperature difference. Is the ground warmer than the air above or cooler than the air above? That tells you the sign, so it can be positive or negative. And it also depends on the wind speed. If you have no wind, there will be no sensitive heat flux. And that's an important feature on smaller scales. If you think about cooling effects or so, you need the wind exposure as well. Okay? So these are the additional components that you need to learn about in order to understand features like the heat distribution in cities. Yeah? And you also learn about the global surface heat balance. Okay, we talk about it. Okay, so now let's have a look at this table, because this table includes now these symbols. Okay, you can see this one is from the Hartmann book, and you can see in this table there is something here: the net radiative heat flux that you have. Latent heat flux is shown here. LE is the latent heat flux, and SH is the sensible heat flux. Okay, in this notation. And in this table, what is compared are the continents versus the oceans. And let's have a look at the continents, all land. Before we do that, just quickly, it's important to know what the sign means. Okay, here the positive numbers of the latent heat actually refer to a cooling effect, and also the positive numbers of this one here of the sensible heat flux refer to a cooling effect. So if you compare this now, you can see that the radiation gives you a warming effect, all land, on its own, but it's compensated half by the latent heat flux and half by the sensible heat flux. So that's over land, sensible heat flux, and latent heat flux. Both together balance the surplus of radiation that you get. Over the oceans, it's actually the latent heat flux which balances most of the surplus radiation that you get. That's fascinating, isn't it? How big a role evaporation plays over the ocean. And indeed, at the sea surface, you always have a fully saturated 100% humidity. And so you can expect that you have a big latent heat flux here. So the interpretation is, First of all, the net radiation over the oceans is 70% larger than over land. The evaporation balances 90% of radiation over the ocean. Over land, evaporative and sensible heat fluxes are about equal. Okay, so you learn about the significance that evaporation makes, and you can directly relate this knowledge now to your microclimate knowledge. You just need a water feature. If you build somewhere a house, you do it near a water feature, may it be a creek or a lake, something else, or a swimming pool, whatever. It has a big effect on the microclimate in your region. All right, let's see what else we do here. What we also do is, now let's see what comes on the next slide. We look actually at the residual surface heat flux on Earth, adding latent heat flux and sensible heat flux to the equation. Okay, and here again you have to be a little bit careful with the signs. But let's see whether you can now you can understand that. So what's shown here is the distribution of components of that surface heat flux budget from the South Pole to the North Pole. So in this graph, you have an x-axis which goes from -90 to +90, from the South Pole to the North Pole. And then is shown the distribution in watts per square meter of these terms. RS is the radiation balance that you get. Okay, you get the radiation balance, okay, which has a big positive near the equator, and becomes actually very small near the poles, and that's because of the albedo effect. You have white surfaces, ice, and lots of albedo, so you get really a very, very small residual heat flux in polar regions. Okay, so now the big part that balances this is the latent heat flux, and why it's so big is simply because 75% of the surface is ocean. Okay, and you just learned that it plays such a big role. So that's what you get, and it has a little dip near the equator, and you'll learn more about later on why that is. Why the latent heat flux is smaller near the equator. So this is the big balance. Another cooling effect comes, and there is it's a smaller contribution comes from the sensible heat flux. So now if you put all these terms together and you work out what is your net surface heat flux, you get this curve here, which has a surplus, a warming effect, okay, in the tropical near equatorial regions, say from -20, from 20 degrees south to 20 degrees north. This is where you get a surplus, a warming effect. And at mid latitudes, you have a cooling effect. Okay? A cooling effect between 20 and something like 70 degrees north and south. Okay? And this is you get on an annual basis, and it actually becomes compensated by both oceanic currents and also wind patterns, okay, in the atmosphere. So that is not that the equatorial regions get up warmer and warmer and warmer and warmer, and middle latitude regions get colder. It's now, this is the driver of winds and oceanic currents, and that together actually result in an equilibrium situation on Earth. So it's quite complex if you put all the pieces together of the puzzle. If you think about what determines the surface temperature on Earth, it is a complicated story. Okay, and this is the end of the second part of this lecture.